Hey, my name's Matt, and this is my son. His name is Conrad Cross, and he is perfect in every way. Except for one thing. He can't walk good. Actually, two things, because he can't read either, but that's a different story.
There's writing on the blade of this sword, but if you want to know what it says, you're out of luck. And that's because I can't read it. He's a VTuber. He can't read.
Let's focus on one thing at a time. I can fix him. In many AAA games releasing today, it's typically pretty important that the main character can walk on a surface. Actually, this is somewhat easy. Just slap a walking animation on there, start it when the character's velocity increases, and boom. You're done. Conrad can walk. But, wait a minute. What's that? And what is this? We can't have you doing that, my son. It's just not professional. We're going to need to dive a little deeper to solve this problem by creating a system in our game engine which helps our poor boy get over his issues with slopes. To do that, we're going to talk about the wonderful world of inverse kinematics, a topic I see popping up quite a bit in the animation space nowadays. Inverse kinematics, or IK for short, has a lot of practical uses during gameplay, like making the player character hold something, look at something important, or hold on to ledges while climbing. But today, we're going to talk about Conrad's feet. First off, what exactly is IK? If you're interested in a really awesome case study and explanation as to how it's used in the game Shadow of the Colossus, I highly recommend this video from Dan over at PlayFrame, a sister channel to the highly popular NewFramePlus. It's a great analysis that covers a lot from the perspective of an animator, so definitely check it out. My explanation might fall a bit short by comparison, but to put it simply, inverse kinematics is a system that allows you to define an endpoint for an appendage, such as an arm or leg, and have each joint solve for a particular rotation that allows the point to be reached. Without IK, an animator trying to make a hand connect with something would have to manually rotate each joint to find the perfect angles which allows the hand to reach the position they want. With IK, they would simply need to place the hand at a desired position, and the bones connecting to the hand will rotate to match. It might sound like a small improvement, but believe me, it saves a ton of trial and error time over the course of development. Let's take a look at a simple example in the 3D modeling program Blender. Here I have a chain of what we call bones, which defines the joints for a particular character rig. If I want to animate these bones, I can rotate them, and try to get the end of the chain to line up to a specific position. But if I add the inverse kinematics bone constraint to the last bone, I can choose a different bone as a target and it will try its best to reach it. I have the ability to increase or decrease the chain length, which defines how many bones will get affected by the IK. You can see that with a higher chain length, we have a greater range of motion, because more joints can contribute to the mathematical solution running behind the scenes. Note that the bones don't even have to be connected, because their relative rotations will be used as a baseline. Take a closer look at our boy Conrad in Blender. It's the exact same setup that I showed you, but applied to an arm. We can see that the last bone before the hand has an IK constraint, and the target is set to this fake hand object. For ease of use, I also made the hand copy the rotation of the fake hand so that I can just use this one bone to animate the whole arm. We can see the same setup reflected in Conrad's legs. I use a fake foot to drive the motion of the appendage, but here I also use a knee bone. There's actually a second IK constraint placed on the thigh bone targeting this knee, and this is so that I can angle the leg for more precise control. So we've just seen that stacking multiple IK systems works perfectly fine, and all of this working together gives the animators tons of options for posing a character more easily. Now that we know what inverse kinematics is capable of, we can apply it to Cross so that our animation process is faster and more manageable. As we saw in the previous section, when an animator wants to create a walk cycle, they'll often utilize IK within their 3D editing software, like Maya or Blender, to help position each foot on the ground or above the ground, depending on which frame they're currently posing. But there's a problem. When Conrad learns how to walk on a flat surface, that animation is saved and imported into the game engine. As we saw earlier, if we integrate this animation and move Conrad down a slope, his feet have no chance of lining up with the ramp, because he only learned how to walk in a straight line. Sad. Alright, so what can we do to combat this? One method is to create another animation for walking down a slope, and then blend between the two, depending on the angle of the floor surface. Great, that works, and some games do go this route, but I'm sure you can imagine all sorts of scalability issues at this point. Like, what happens when you need to go up a slope instead of down? We'd need another animation. What about sidestepping on a slope? We need the feet to be pointing down, so that's another animation. Sidestepping in the other direction? You get the picture. This is just way too many animations to realistically create for every single type of rig in our game. We need a better method. To solve this, it'll be useful to learn about another layer of IK that is typically applied outside of the 3D editing software, something I'm going to call runtime IK. This is inverse kinematics applied programmatically within the game engine itself while the game is actually running. In other words, it's not baked into the animation file that the animator puts together when designing a walk cycle, but is instead calculated on the fly via code, and a lot of math, to change how the character joints rotate in the game itself. So with runtime IK, we can modify the leg rotation based on the environment that Conrad encounters, to make his little feetsies match up with the slope in real time. With that knowledge, we only need to animate for flat surfaces, and let the power of programming do the work of matching it to the ground he's currently standing on. There's just one problem. Now we have to do the programming. Don't worry, this is the fun part. As gameplay programmers, we're tasked with building an inverse kinematics detection system, so that my son Conrad can take advantage of IK for foot placement. Now, I'm used to the animation systems available in Unity, but the same principles should apply to any other modern game engine. All you really need to implement something like this is an IK solver, some inputs to affect the IK solver influence, a physics API, and a reference to the character joint positions. Don't worry, we're not going to be doing the math of figuring out joint rotations, we're just going to be building a weight manager that controls the existing IK system by feeding it influence and target values. Let's break down our problem into 3 steps. For any given frame, we need to know 1. How much influence our IK system has over each leg. Now, why is this needed? If the system had 100% influence all the time, the character would be dragging their feet through the entire walk cycle, and none of the original animation will be visible. We need to be able to turn it off to allow the animator's work to shine through. And 2. Where the IK target is for each leg. The point of this system is to adapt the animation for any surface, which could change in position or angle at any time. We'll have to figure out how to detect that change and how it affects the target position and rotation. 3. Any other adjustments to the character to make the IK look natural. It's easy to just throw in some IK targets and call it a day, but we'll soon find that we can end up with a lot of stretching and mechanical motion if we don't use a few extra tricks to smooth things over. Let's start with the first step and delve into some code. I'll make a new script for this and assign it to my boy. Don't worry, Conrad, we'll get you on that slope in no time. First off, I'm going to lay out some useful stats and references that I know we're going to need. In this game, the animator is held in a separate character script, so I'm just going to grab that so we can assign IK values to it. Also, in Unity, you need to attach a script directly to the animator to get the onIK callback, and I've already made a script that passes that event forward, so I'll grab that too and assign our custom callback to it. This is important because Unity asks that we only set the IK position and weights from this callback, so we'll just keep that in mind. Also, if you haven't already, you need to make sure your animator has the IK pass enabled for the layer that has your walking animations. Let's see what happens when you start off with 100% weight for each foot. Nothing, I guess. Let's try setting an IK position target at vector 3.0 and see if that makes a difference. It did. I know this looks strange, but now that we know our IK system is at least working, we can make things a little easier for ourselves by collapsing these steps into a helper function for each foot, where we set the weight, position, and rotation all in one sweep. And we'll just verify that it still works as expected. Looking great, Conrad. The method I'm going to teach you involves automatically determining the height of the foot as the animation plays, and using that to adjust how much weight each foot should have. For example, if the foot is say 0.2 meters above the ground, we should obviously not be using IK, so we want to decrease the weight. But if the foot is 0.1 meters above the ground, we want to increase the weight so that it can match the floor. By doing it this way, we don't have to rely on manually setting weight values for each part of the animation. We can just let the actual height of the foot drive how much it should rely on IK. I want to note that there are downsides to doing it this way, but this is just a simple example, and in this case, the upside is that this is a more scalable workflow that doesn't involve us defining IK weights for every animation our character could use. We can detect how far the foot is above the ground by using a physics ray, or raycast as it is known in many physics APIs. Specifically, we're going to be using a sphere cast, which adds a radius to the cast, which will detect collisions easier even if there are very precise holes in the floor. So I'll set up a sample function to perform the sphere cast. We're going to need a few inputs to do that. First, we need the start position of the cast, then the distance, which I'm going to set to a hard-coded value, and then the raycast hit info, which serves as the output. I also realized here that I need extra return values for when we do hit, as well as the position and rotation of the surface for later, so I'm going to add those as out values. This just means that I can modify them and the code calling this function can see the changes reflected outside of the function. Great, now we can type our sphere cast and we will plug in the start position, the radius of the sphere, and the direction, which is just downwards relative to the player, and also the distance. I also realized that we need a layer mask, so I'll quickly define that above. This just tells the sphere cast which layers to ignore during the check. Within the sphere cast, we can set the hit ground value to true, grab the normal direction, calculate the rotation based on the normal direction and the rotation of the player, and then return the hit position. This ended up being a weird way of doing it. I probably would have preferred to return these values in a struct or something, but I was just adding on functionality when I needed it, so it doesn't matter too much for this example. Okay, now we can call this function for each foot, and we'll have to set up the input values that we need for it. One neat thing about the animator component is that we can just request the foot bone transform based on an enum if you're using a humanoid rig, so this saves us the trouble of having to manually reference it. There's one more problem though, which is that we're sampling the bone position to do the sphere cast. The position is already affected by the IK system. If we keep it like this, we're going to end up with a positive feedback loop, where once the foot hits the ground, it will always stay there since we're never sampling the position defined by the original animation. To fix this, we can simply set the weight for each foot back to 0 before doing the check, and then our later code will set the weight properly. Since it happens at the end of the callback function, that will be what we actually see visibly in the game when the frame actually renders. Now let's rip our ground hit bool out of this function so we can use it elsewhere, and also store the weight value in a more global variable so it can change over time. In update, which happens every frame, we will set a target value based on the ground hit bool and move towards it with the speed value that we defined at the beginning. Awesome, let's plug in these new weight values and see how it works. After fixing up a few heuristic values like the distance and start position, we can see it in action. This looks wild, but it is working as expected. You can see that as the animation moves the foot up and down, the IK weight of each foot increases and decreases, even though the position is still wrong. We're nearly there. This step is really easy since we already took the time to capture the hit point and rotation when we performed our sphere cast. So we just have to store the position and rotation values in the data class and set them if we get a ground hit for each foot. There are definitely cleaner ways to do this, like if we had a data class for each foot, we could more easily fit these values into a more scalable data structure, but this works for now. Now we just have to plug in these position and rotation values and we have a working system. It looks a bit strange, but it is working properly now. You can see that the weight turns on and off as Conrad moves forward, and his feet are rotating to match sloped surfaces in some situations. Now it's far from perfect, and I'm going to do a bit more tweaking here to get the heuristics in check, but what you've just witnessed is the foundation of the actual IK system that I use in my game. There are just a few other tweaks we should make to really make it shine, because as it is now, this actually looks kind of worse than just not having an IK system. That's not something we want. Let's fix those eager legs of yours, son. I've switched over to the actual IK script that I use in my game, and you can see the difference that a bit of polish does. Again, this is using the exact same foundation that we just coded, but cleaned up with a lot of extra bells and whistles to handle different edge cases. Bet you're curious to know what those are, right? No? Well, Conrad Cross sure is, because he's very happy to finally make full use of his legs. You may have noticed a bit of sinking when the feet encountered a steep slope, and this happens because the base of the foot is not the point of rotation. To fix this, we can use heuristic magic to simply move the final position upwards by a certain amount depending on the final rotation of the foot. The weights are much more finely tuned to turn on and off at appropriate times, and this is done by playing around with the speed values and adding extra conditions for the weight to be turned on. One of those conditions is the rotation of the foot, because if the animation tells it to point downward, then we don't have a good way of keeping that original intent in combination with a slope. So instead I opted to simply reduce the weight in that case. To clean up the running animation, I also reduced the weight faster if the foot is too far behind the character, which is a good indicator that it's not on the ground. However, if we change the weight too fast, it appears to snap into place, so there's a careful balancing act. One last thing I didn't do in my current project, but did do in my game Iron Reckoning, is to adjust the root position of the character's hips when there is an extreme difference in position between the 2 feet. For this character called Jaina, I detected when the IK position was too extreme, and gave one of the legs more room to work with by moving the hips downward. This happens smoothly over time, so even in motion, if one foot is sinking down to hit a lower platform, we can simulate the shift in the center of mass depending on the surface, which really helps to make sure we're not stretching the leg too far. This is really only necessary for more extreme situations, like in an action-focused game with a lot of dynamic floors, like the kind you'd find in Iron Reckoning. Well, there we go. We finally helped Conrad to get over those pesky slopes, and he is proud of what we were able to accomplish together. Let's give ourselves a pat on the back, knowing that we helped this poor little boy get over one of his greatest fears. And now let's reflect on this learning experience, and think about how we can apply this to more situations and different types of walk cycles, say on less humanoid characters. Or we can think about how we can apply this to a climbing system to make arms and hands realistically attached to holding points. The possibilities are endless, and I'll leave the rest up to you. You know what? I think this means that Conrad Cross isn't just my son. He's our son. Let that sink in. If you want to see your new son in action, do check out my upcoming game Burden of Truth on Steam and hit that wishlist button. That is the only way you can show affection for your child. So do it before you regret your life choices. If you want to see more, feel free to subscribe or follow me in these other places. And as always, thanks for playing. See you in the next one.